Hello everyone. Today, we'll be delving into a fundamental concept in deep learning, batch normalization. This technique has revolutionized the training of deep neural networks and has become a staple in modern machine learning workflows. Let's dive in. Let us quickly have a look at the topics of today's discussion. Batch normalization was introduced to the world of machine learning in 2015 by Sergey Yaffe and Christian Szegedy. Its primary aim is to address the challenge known as internal covariate shift, which can hinder the training process. Let's explore how batch norm tackles this issue and transforms the way we train neural networks. Now we will dive into a fascinating phenomenon that affects the training of neural networks. It's called internal covariate shift. This term describes the scenario where the distribution of activations within a neural network layer undergoes changes as the network learns. Picture this: during training, the parameters of the earlier layers are continually updated. However, this dynamic process leads to varying distributions of inputs for subsequent layers. This variance can impede the training process, causing slower progress and complicating effective optimization of the network. Enter batch normalization, our hero. By skillfully normalizing the activations within each mini-batch during training, batch normalization steps in to counteract the challenges posed by internal covariate shift. The result? Quicker, more stable convergence that transforms the way we train neural networks. In the process of data normalization, we set the mean of each feature to 0 and its variance to 1 before feeding it into a deep learning model. The reasoning behind this practice is to enhance the model's performance. When data is normalized, all its features share the same scale, granting the model an optimal environment for learning. It's worth noting that normalization is applied independently to each feature column. We calculate the mean and variance of each feature column across the entire dataset, ensuring a consistent and balanced approach. Take a look at this image illustrating the impact of data normalization. The initial data values, depicted in blue, have now been shifted to be centered around 0, displayed in red. This alignment guarantees that all features share a uniform scale. Initially, the data values were spread across a broad range, possibly hampering effective model learning. However, after normalization, all values converge around 0 with a variance of 1. This adjustment simplifies the learning process, enhancing the model's performance significantly. Let's focus on any hidden layer within a network. The inputs to this layer stem directly from the activations of the previous layer. To illustrate, consider layer 2 in the diagram below. If we blank out all prior layers, the activations originating from layer 1 are indistinguishable from the initial inputs. The rationale that drives the normalization of input for the first layer remains valid for these hidden layers too. This insight paves the way for the utilization of batch normalization across any layer within a neural network, not just the input layer. In essence, by normalizing the activations stemming from each preceding layer, we facilitate more effective gradient descent during training. This is the precise role accomplished by the batch norm layer. Similar to the parameters such as weights and biases found in any network layer, a batch norm layer also features its distinctive set of parameters. Two parameters, beta and gamma, are learnable and can be adjusted during training. Additionally, there are two non-learnable parameters, known as mean moving average and variance moving average. These are retained as integral components of the batch norm layer's state. Importantly, these parameters are specific to each individual batch norm layer. Consider a scenario where the network comprises 3 hidden layers accompanied by 3 batch norm layers. In such an arrangement, we would encounter 3 sets of learnable beta and gamma parameters, each pertaining to its corresponding layer. The same principle holds for the moving average parameters associated with each layer. While the network undergoes training, it operates on a single mini-batch of data at a time. In the forward pass, each layer of the network handles this mini-batch of data. Specifically, the batch norm layer executes its data processing in the following manner. Let's break down the batch norm process step by step. 1. Activations. The activations from the prior layer serve as input to batch norm. Each feature in the data corresponds to an activation vector. 2. Calculate mean and variance. Individually for each activation vector, the mini-batch's mean and variance values are computed. 3. Normalize. Normalization involves computing normalized values for each activation feature vector. These normalized values now boast a zero mean and a variance of 1. 4. Scale and shift. An intriguing aspect of batch norm is its capacity to adjust normalized values. Learnable parameters come into play. The normalized values are multiplied by a factor called gamma and then augmented with a factor, beta. 5. Moving average. Batch norm doesn't just stop at the moment, it also keeps track of normalized value means and variances during training. These statistics prove invaluable during inference, even when the distribution of input data changes post-training. This process equips batch norm to efficiently enhance network training and inference. In training, batch norm computes mini-batch mean and variance. Transitioning to inference, where only a single sample is present, the previously calculated moving average parameters take center stage. These pre-calculated values optimize batch norm's performance during inference, sparing the need for resource-heavy full dataset calculations. The use of moving averages ensures efficiency by focusing on the latest values. There's a debate about where to position the batch norm layer within the architecture, before or after activation. Here are some examples on how to apply batch normalization. Let's explore the benefits of batch normalization. Accelerates deep neural network training by minimizing internal covariate shift. Activations are normalized, ensuring stable activation distribution. Facilitates higher learning rates, expediting training. Stabilized gradients simplify learning. Enhances generalization performance. Reduces sensitivity to weight initialization. Lessens reliance on regularization techniques like dropout and L2 regularization. Stabilizes training, curbing overfitting risks. Let's explore real-world applications. Google researchers leveraged batch normalization in 2015 to enhance their image classification model, Inception v3. Batch normalization improved speech recognition models in Amazon Alexa and Google Assistant. In 2017, a study showcased a deep learning model with batch normalization achieving 97.6% sensitivity and 96.6% specificity in detecting breast cancer from mammograms. In 2019, a self-driving car integrated with batch normalization exhibited superior obstacle detection and avoidance accuracy compared to a car without batch normalization. Let's uncover some practical tips for using batch normalization. Apply batch normalization post-activation functions, example, RealU, sigmoid, to stabilize training by normalizing activation distributions, especially under nonlinearities. Tune momentum and epsilon parameters in batch normalization to influence moving average and variance. Experimenting with these can optimize network performance. Selective application of batch normalization can be effective. Experimentation with configurations enhances network performance. Favor large batch sizes for optimal batch normalization performance. Smaller batches might lead to inaccurate moving averages and variance, potentially impacting training. Let's explore some limitations. Batch normalization requires a large batch size for accurate moving average and variance calculations, crucial for effective training. Using batch normalization might reduce network robustness to input changes, as normalized activations can diminish sensitivity to fluctuations, especially if data isn't normally distributed. Additionally, it can hinder interpretability, introducing a nonlinear transformation that complicates understanding network operations. Here is a list of some alternatives to batch normalization: group normalization, GN. Switchable normalization, SN. Attentive normalization, AN. Stochastic normalizations as Bayesian learning. Weight normalization. These references offer a wealth of knowledge and insights for those eager to delve deeper into the world of batch normalization and its applications. Remember, the world of deep learning is ever evolving. and understanding techniques like batch normalization equips us to navigate its complexities effectively. Thank you for joining us on this exploration.